Okay, so the sun is emitting a flux by radiation. In order to calculate the emitted flux by radiation from the course is calculated as following. Epsilon, which is the emissivity of the body, times the Boltzmann constant, which is a constant. A is the area of emission, and T is the temperature of the surface. So here, they said that the emissivity is 1, so the sun is a black body. It's a very good emitter. And sigma is constant, is equal to 5.67 times 10 to the power minus 8, so it's always this value, times, now what is the area of emission? The sun is in the form of a sphere, and they gave us the radius of the sun, okay? So what we want is the external area, if you want, okay? So the area of the sphere from the outer side, which is equal to 4 pi times radius of the sphere square, okay? So this is RS. So if you want, it's the external lateral area of the sphere. It's calculated as 4 pi RS square times the temperature of the sun, which is given as 5,800 Kelvin to the power 4. This result will give us the total emitted flux by the sun. Okay, so this is the rate of energy emitted by the sun. Now, the next step is I want to find the power per meter square incident at the equator. Now, what I should pay attention for, I should know that when reaching the equator, what will be the total surface, if you want? Look, when I have the expansion, then to reach this point, I have, if you want, like a very big circle. So let me try to draw it another way. So my purpose is to reach this point, okay? So as you can see here, in watt per meter square, of course, as I go far from the sun, the intensity will be reduced, okay? Because the smallest external surface area is at the sun level. As I go far from the sun, the energy will be distributed over a larger surface. And when reaching the Earth, I can consider that the distance separating the sun from my Earth. Okay, so here I have the radius of the sun, and I have the distance between the Earth and the sun, which is given here. So distance between Earth and sun. Now, it's true that I am interested to find this full intensity at the equator level, but you know that the radius of the Earth, okay, is much smaller. It's much smaller compared to the distance between the Earth and the sun. This is why I can neglect the radius of the Earth compared to the distance between the Earth and the sun. Okay, this is why we can here treat it nearly as a point. For the Earth, we can treat it as a point because the radius of it is nearly much smaller than the distance separating the Earth from the sun, and much smaller than the radius of the sun. Okay, this is why here we neglect it. You can take it, of course, into consideration, but it will not affect a lot your result. So if you want to be very accurate, then since you are interested to what is happening at the equator level, you should add to this distance the radius of the Earth. So you can say that the distance of the big sphere that I am interested in is equal to DES plus radius of the Earth. But this will not affect a lot the result because, as we said, we can compare this term compared to this one. Now, the next step is to find what is the intensity. Okay, what is the intensity at this point? To find the intensity at this point, we know that the total flux is the same. So the flux in watt emitted is the same. But what is different now is that this flux is divided over a much larger area, lateral area. So now, to find the intensity of the flux, So we will write that the intensity of the flux, intensity, or if you want, you can call it the power per meter square, okay? Intensity, which is power per meter square, is equal to the flux emitted, which was calculated here. So it's flux of the sun, okay, over the receiving area, over the total receiving area. Now, what is the total receiving area? What is the total receiving area here? You have
the surface of the Earth.
Yes, you have the what? Can you please repeat?
The surface of the Earth.
It is half the surface of the
No,
Earth.
no. Look, what I mean here, what I mean by the receiving area, I mean this one. Look, this is the flux of the sun. Yes, I understand what you mean. You mean after it will reach the Earth, okay. But now what I am calculating is the following. To calculate the intensity, as you can see in this figure, not all at the end, not all the flux emitted by the sun will be received by the Earth, okay? Because look, the sun will emit for a very big radius, and it will reach the Earth just at one point, okay? But when it's reaching, of course, it will reach the Earth at the different points of the Earth. But what I am interested in is to just calculate at a certain point what will be the intensity. So I will not divide by the surface of the Earth. No, I will divide by the total receiving area. So the Earth is one point in my very big area, if you want. Okay, so the total area receiving is here 4 pi times the big radius square, and the Earth will take this intensity will be also on the Earth. So once I calculate this intensity, it will be the intensity on the Earth and the intensity on any body that is at this distance from the sun. So now if you take any satellite, or if you take any other object than the Earth, if you take it here, for example, and it is at the same distance from the Earth, it will receive the same solar intensity. Of course, neglecting obstacles. Yes.
How did we choose again the surface receiving?
How we choose what?
The receiving surface.
Okay. How we choose the receiving surface? Look, to know what we mean by the receiving surface, okay? You should look at what is happening with the emitted flux of the sun. The sun is emitting in all directions, yes or not?
Yes.
Okay, so it will if you want, the solar rays will reach the Earth and can reach any other object, not only the Earth. Okay, so you can have
Yes.
objects.
Okay, but why 4 pi?
Why 4 pi? Because it's propagating. It's propagating in a spherical way. Okay.
Yes.
And how you find the lateral area of a sphere? What should you do? It's pi. It's
the
4
same
pi
thing.
also.
Yeah,
Okay?
the same thing that we
Yes.
did for the sun.
Very good, as you did for the sun. And the only idea, if you want to understand it better.
We're making the sun become more closer to the earth.
Yes,
we're making the
exactly.
sun
So
closer
if
to
you
the
want, more you are far from the sun, the intensity will be lower because you are dividing your flux into a larger area. And now if you take objects that are more far than the earth from the sun, also the intensity here will be smaller. So the maximum intensity will be at of course, at the sun level. And the farthest you are from the sun, you will have a smaller intensity. Now, we are interested in particular for the Earth because it's our planet. So here we are just interested in the intensity reaching the Earth. To know the intensity reaching the Earth, we should consider the sphere centered at the Earth and having as radius the radius of the Earth plus, or if you want, just the distance between the center of the Earth to the equator level.
sun.
Okay, but here because the radius of the Earth is much smaller than the distance between the center of the sun and the surface of the Earth, we neglected the radius of the Earth. Okay, If it's not yet clear, I can repeat. I can try to repeat in another way.
Okay, thank you.
Okay. Now, so what we found until now is the intensity at this level. Okay. The intensity at this level is the total flux divided by the big receiving area. Okay. So the big receiving area is 4 pi times the distance between the Earth and the Sun square. Okay. So now if we do the calculation, we obtained 1,379 watt per meter square. This is the solar constant. Now, I know that it was a little bit confusing for you, the difference between this receiving area and what we were talking about before. I will now repeat, okay? Now, once you find the solar intensity, okay, this solar intensity, it's true that the Earth is nearly a point with respect to the Sun, but whenever you go to the Earth now, so now if I go back to my Earth, okay, at each point, I will have, of course, if we don't consider obstacles, we don't consider the atmosphere, at any certain instant, half of my Earth will be subjected to the solar intensity. Okay, so this is my case. And at any point, what is the value of the solar intensity? It's 1,379 watts per meter square. Okay, so now if you want, if I mean by receiving area, when I deal with my Earth, I have solar intensity over this whole surface. And when I want to calculate the total flux that is absorbed, as I said, the horizontal component will cancel each other. And the total vertical component, so I can consider that my Earth in total is absorbing a net flux in the vertical direction. And from mass, the net flux will be equal to the solar intensity times the area, times this area, which is the cross-sectional area at the equator level. Okay? This is why, after I find the intensity, I will be able to calculate what is the flux absorbed by the Earth. So I can say that phi absorbed is equal to the solar intensity, so solar constant, okay, times the cross-sectional area at the equator, which is pi times radius of the Earth square. Okay? Clear? Any question on this? Okay. Now, let us apply now what we have seen in this problem. We will apply it to understand in calculation what is the greenhouse effect. Okay? If you remember, we said that the greenhouse effect is due to the absorption of infrared radiation by the atmosphere. And this will can cause a raise of the Earth's temperature by nearly 35 degrees. Okay? So we will see together now that the atmosphere can play a positive role, because we will do some calculations and we will show that if we don't have the atmosphere, what will happen. And we will see that if we don't have the atmosphere, the temperature at the Earth will be very cold. So it's not good. So the atmosphere has a very positive role, that is to keep a comfortable temperature on the Earth. But on the other hand, if the rate of emissions of greenhouse gases as CO2 is very high, which is the case during combustion of fuels, etc., this will cause to block the infrared radiation emitted by the Earth, and they will go back to the Earth, which will tend to increase a lot its temperature. So we will see that if it will not play any role, if we don't have an atmosphere, it's not good. And if we have a lot of greenhouse gases, also it's not good, because we can reach very high temperatures. And we will understand this by calculation in this example. Okay? So the solar radiation that is incident on the Earth's atmosphere, as we have calculated now, has an intensity of 1.37 kilowatt per meter square. Okay, this is the solar constant we calculated together now. And we said that to calculate this constant, we assumed that we don't have anything, any obstacle between the sun and the earth. But in reality, it's not the case. Okay, this is why they are telling you now that the fraction reflected back is close to 30%. So only 70% is in reality transmitted. Okay, now what would be the surface temperature of the earth in two cases? We will compare two cases. The first case, the earth's atmosphere did not absorb any of the incident solar radiation nor any infrared radiation emitted by the earth's surface. So in the first assumption, we consider that the atmosphere is not doing anything, it's just transmitting. Okay, so it will transmit solar radiation and then it will transmit infrared radiation. It will not reflect back to earth. Okay, the second question is in part B, the atmosphere will absorb all the emitted radiation by the earth and it will still transmit solar radiation. We will see what is the difference between the two examples in calculation. Okay, so first, they are giving you a small note, and this note is what we have talked about in the previous problem. The incident solar intensity is absorbed by an area equal to pi times radius of the Earth square, okay? Because this is the cross-section facing sun. So here they are telling you, after I know what is the value of the solar intensity, if I want to find at a certain instant what is the energy absorbed by the Earth, I should multiply by the cross-sectional area, which is pi r e squared. Now, this energy is absorbed at this level, but you know that in steady state conditions, what is absorbed should be radiated again, because if it's only absorbed, it will lead to a very high increase in temperature. So when we reach steady state conditions, we reach constant temperatures. In this state, what is absorbed will be radiated back, okay? And this absorbed portion that will be radiated back will be radiated through which surface? So imagine this is your Earth, okay? This is the Earth. The Earth absorbed a certain flux and now it wants to radiate it back. It will radiate this flux through which surface? As the sun was doing, it will radiate it over the entire surface. And what is the entire lateral surface of the Earth? It's a sphere.
4 pi r square.
Exactly. So it's a sphere. So now, if I want to calculate, if you want the radiation flux per unit area, what should I do? I will say that the Earth is absorbing the following amount. It's absorbing S, which is the solar, in case, of course, if you want S here represents the flux that is reaching the Earth. Because we said that it's not the complete solar fraction, solar intensity, because the atmosphere will reflect a certain proportion. Okay, so we will do this in calculation now in this problem. So this is the absorbed heat. Okay, the absorbed flux in watt, and then if it will radiate back, it will radiate over the total lateral area, which is 4 pi r Earth squared. So the solar intensity of radiation, okay, the intensity of radiation is the solar intensity reaching the Earth over 4. Okay, so let's say if we assume that 100% is transmitted to the Earth, we don't take the effect of the atmosphere, then the solar intensity will be 1.37 kilowatt per meter square. Okay, if 100% is transmitted, no reflected proportion, but it's never the case. Okay, as you can see here, nearly 30% is reflected. But in the extreme case, then if I divide 1370 by 4, I get the intensity of radiation emitted back by the Earth, which is 342 watt per meter square. Okay, so of course the intensity of emission of the Earth will be smaller than the solar constant because of the areas. The absorbing area is pi r e square, while the emitting area is 4 times pi r e square. This is why the intensity is reduced. But as we know, atmosphere will always reduce the fraction. So we never have the complete, this is the maximum ideal number we can reach, but in real case, we never reach it because always we have a certain reflected fraction by the atmosphere. And also, you know, the atmosphere is not uniform. So you have some parts that have concentration of CO2 different than others. This is why for the Earth, some areas will receive a higher income solar radiation than others. Now, in numbers, we will see what is the effect of the atmosphere on the temperature of the Earth. Okay, we will start first by the first assumption. The first assumption is that the atmosphere only reflects sunlight. It will not absorb any, infrared radiation of the Earth, and it will not emit back to the Earth. This is the first assumption. So what will be the scenario here? First, you have the solar incident flux coming from the sun. Okay, you have at this level, before reaching the atmosphere, what is the solar intensity? We assume that the solar intensity, look here, the solar intensity at the atmosphere is assumed to be equal to the solar intensity at the surface of the Earth, because the distance between the surface and the atmosphere is also much smaller than the distance between the atmosphere and the sun. So always here we do some assumption that can neglect, because you have very small numbers that can be neglected. Okay, this is why they assume that solar intensity at atmosphere is nearly equal to solar intensity at surface of the Earth, because the distance between them is negligible compared to the big distance. So now they told us that the reflection coefficient by the atmosphere is 30%. This means that if I have a solar flux incident on the upper atmosphere equal to S, 70% will be transmitted by the atmosphere and 30% will be reflected back. Okay, so you have this flux here. This flux is divided into two parts. One that is transmitted, so the atmosphere will not do anything, it will just transmit a portion, and the other portion will be reflected up. And as you can see, by conservation, if this is S, okay, if this is 30% of S, this should be 70%. So here we have that 0.3 S is reflected back to the outer space, while 0.7 S is transmitted. Okay, 0.7 S is transmitted. So now the solar flux reaching the Earth is 1 minus A. Okay, and please, you should pay attention for terms. Transmission is different than absorption. So here at this stage, the atmosphere only transmits the heat of the solar heat. It will not absorb it, because if it will absorb it, it will affect its temperature. And they told us that it's just transmitting. So here the atmosphere, if you want, it is transmitting heat, not absorbing it. Okay, so you can assume that it's not here, because it will just transmit it and it will reach the Earth. So now for the Earth, we don't say solar flux transmitted to the Earth, we say solar flux absorbed by the Earth, because the Earth will absorb it. And once it will absorb it, assuming here that it's a black body, so when we say it's a black body, everything absorbed will be radiated again. Okay, so the solar flux that is absorbed by the Earth is equal to 0.7 S, will be radiated back by the Earth. But this absorption will lead to what? It will lead to a certain temperature increase. And at steady state conditions, we will calculate what is the temperature of the surface. So because it's absorbed, we have the temperature of the Earth at a certain level. If it will be transmitted without absorption, then I will have a lower temperature of the Earth. Okay, so here, how can I find what is the temperature of the Earth? What analysis can I do? Who will tell me? I just give you this information. I give you the solar constant. I give you the proportion, and I want the temperature of the surface of the Earth. How can I do this? I should
By radiation.
what?
Get the heat transferred to the surface of the Earth by radiation due to the solar flux.
Yes. So here I can say that the absorbed flux is equal to the radiated flux. Okay? And I can calculate what is the expression of the absorbed flux and what is the expression of the radiated flux. My only unknown will be the temperature of the surface, and I get it. Okay? For the atmosphere, I didn't do any analysis because it's not absorbing anything. It's just transmitting. So it's like it's not here in this case. Okay? So what I will do is I will say that Q absorbed by the Earth, okay, and here everything is Q dot, it's power, it's in watt, okay, so Q dot absorbed is equal to Q dot that is radiated, okay, equals to
Sorry,
Q
I have
yes?
a question.
Yes.
One question, please. The atmosphere, if it's only transmitting the energy,
Yes.
then the temperature will stay the same. Yeah, the atmospheric temperature will
Yes,
stay the same.
exactly. If it is like it's not here, yes.
Yes. Okay.
Okay,
Thank
so
you.
if you want,
Just-
it's not playing any role. It's just,
Okay.
it's like just an empty space, if you want.
Okay. Otherwise, some energy might be lost. يعني okay, I understand.
If you want, look, even if it will not be lost, but if you want, once it's absorbed and then radiated, it will affect the temperature. And you will understand this better when we do the comparison with the next case. Okay?
Okay, sure. Thank you.
So if you want, if you don't know what is the atmosphere temperature, if you don't know it, you cannot calculate it here because it's just transmitting. It's transmitting what the flux. It is not affecting it in any way. Okay?
Yes.
So as you
Yes,
said,
yes.
it will keep the same temperature.
Yeah, sure. Okay, thank you.
So now we have Q dot absorbed equal to Q dot radiated. Now, what is the absorbed flux? As we did the analysis together, what is the solar incident? The incident intensity, it's not 100% of the solar intensity, it's 0.7 S. Okay, so to calculate the absorbed flux, it's 0.7 S times, we said that what is here, what is the area absorbing this flux? If you remember, it's the cross-sectional
Pi
area
R
at the
Pi
equator
r
line.
square. It's
Very
pi
good.
r square.
Yes, exactly. So I multiply by pi times radius of the Earth square. This is my absorbed flux. Okay? Now, equals to, as we said, we have steady state conditions. So what is absorbed will be radiated back. Now, what is the radiation flux? It's equal to the emissivity of the Earth. So emissivity of Earth. And because they said assume that the Earth is a black body, then the emissivity is equal to 1. Okay? So I replace epsilon by 1. Then I should multiply by what? I should multiply by the 7 Boltzmann constant, which is sigma. Okay? Times what now? Times the area that is radiating. What is the area radiating? It's 4
pi r
pi.
square.
Yes, it's 4 pi. So times 4 pi times radius of the Earth square. Okay? Times what? Times the temperature of Earth to the power 4. Okay? I know everything in this equation. My only unknown is what? My only unknown is the temperature of the Earth. And my temperature, the temperature I calculate will be in Kelvin. Okay? Because you know that for the formula for here, you have the Boltzmann constant is related to Kelvin. So the temperature you get is in Kelvin. To transform it to degrees, you have to do minus 276. As you can see, when you did the solution, the temperature you calculated is minus 18 degrees, which is very, very cold. It's a very small, low temperature. So if we don't have the atmosphere here, then life on Earth will be, maybe you don't have, you can, the life on Earth will not be as it is now, okay? Because it's a very low temperature and you have a lot of species that cannot live for under these conditions. So it's not a comfortable temperature at all. This is why the role played by the atmosphere is very important. Okay, but we should not go to the extreme. So the disadvantage is that if we go to the extreme, if the atmosphere will reflect a lot of radiation back to the earth, we will risk now the other extreme, which is overheating. So now we will take the other assumption to see how the action of the atmosphere will affect the temperature of the earth. Before, any question on this part?
Yeah, the T part, the temperature part, isn't it a difference? يعني T final minus T.
No, look, yes, I understand. Look, when you say T final minus T to the power 4, you have
Yes.
an exchange between two surfaces. So if you have two surfaces, one emitting, one radiating, okay, then how you calculate the emitting flux?
Okay.
So here, if you want, instead of, we calculated as absorbed flux, because it's already, and it was calculated as an absorbed flux after reaching the earth. Here you don't have just two surfaces exchanging heat. If you have two surfaces exchanging heat, it's true what you are saying. I will say that the absorbed one, I will consider T to the power 4 of this surface, and you have here two temperature. You have T surface and you
Yes.
have T infinity. Okay?
Yes.
When you do this, the absorbed one is at temperature of this surface, and the emitted one is at the temperature. So if I call this to be more clear, if this is T1, this is T2. What you are familiar with is to say that the net rate of radiation is,
Yes.
I am getting epsilon times
Yeah.
sigma,
Sigma.
okay, times the surface,
Area.
okay, S1, let's say, okay.
Okay.
So it's
T4.
if this is S2, I will call this S2. So it's the same area, okay. It's S2 times T1 to the, so I will take it into factor. It's T1 to the power 4, okay, minus T2 to the power 4. You are familiar
Yes.
with this, okay?
Yes.
What is the difference here? Here you have two surfaces that are exchanging heat by radiation. So if you want to find the net flux of radiation, you should subtract, you should consider that because the emitted flux is in the form of radiation, you will calculate it as epsilon sigma times S2 times T1 to the power 4, and minus epsilon sigma S2 T2 to the power 4, okay? But in this
Yes.
case, this flux here, you calculate it as, instead of being radiated from a surface at T1, this is the absorbed flux. So if you want, you got a different expression for this flux because you have a different situation.
Yes.
That's
Yes.
it.
Oh, it's only one surface here. Yeah,
Yeah,
I understand.
it's only one
Okay.
surface absorbing a certain flux. And what is the expression of the absorbed flux? It's one.
It's the
In reality,
0.7.
you have a surface emitting, which is at the sun level. But once reaching the earth, what was the flux reaching the earth? It's this one. Okay, I can calculate it as following.
Yes, we
Okay.
calculated it. Yes.
Yes. Okay. So it depends on how you calculate this flux here. If you have its expression as it is in the case here, or if you have to calculate it as a flux radiated by a surface. This is the only difference.
Yes. Okay. Thank you.
Okay.
Thank you.
Any other question? Okay. So let us continue. Now we will consider the second case. So in the second case, what is happening? In the second case, they told us that first, they said at the first step, we have the same procedure. So we have a flux S that is hitting the atmosphere. One part will be reflected, which is also 0.3, and one part will be transmitted. So until now, there is no difference between this problem and the previous one. Now, the difference is at this level. The earth will reflect, will radiate if you want. It will absorb, okay, then radiate a flux, okay? But now, what will happen is that the atmosphere will not transmit it. It will absorb it, because you know that we said that after hitting the Earth, the solar waves will change in wavelengths. They will become into the infrared zone. And once they are in the infrared zone, if you have, due to the greenhouse effects, you have that these gases will block the transmission back to the atmosphere, back to the outer space of the flux emitted by the Earth. So what will happen then is that the atmosphere now will absorb this flux and will radiate it back to the Earth. This is why now, instead of saying flux transmitted by the atmosphere, we will say that the flux is radiated by the Earth and absorbed by the atmosphere. So you should pay a lot of attention to your terms. If in the previous example, the flux was radiated by the Earth and transmitted by the atmosphere. So if you look here, okay, it's directly transmitted. So this is the flux radiated by the Earth, and this is the flux transmitted, and here it's transmitted by the atmosphere without any absorption. Okay, transmitted by atmosphere. So as we said, it's like the atmosphere is not here. On the other hand, now in this case, they said that the atmosphere will first transmit solar intensity, but will absorb and radiate back to the Earth the proportion that is reflected back by the Earth. Okay, so you have the radiated amount of energy by the Earth will be now absorbed by the atmosphere. And the atmosphere, after absorbing it, will not emit it to the outer space, because as we said, the greenhouse gases will do a blocking effect. So they will be radiated back to the Earth. So what will happen now, my Earth is receiving at the same instant two fluxes. It's receiving a flux coming from the sun. So this flux is coming from the